The James Webb Space Telescope is one of the most ambitious and complex space observatories ever constructed. It is designed to serve as the successor to the Hubble Space Telescope, expanding our ability to observe the universe in unprecedented detail. The James Webb Space Telescope was launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. Its primary mission is to study the earliest galaxies, stars, and planetary systems that formed after the Big Bang, providing insights into the evolution of the universe. The James Webb Space Telescope represents a collaborative effort between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. The project began in the late 1990s, with the goal of creating a space telescope capable of observing in the infrared spectrum, which would allow it to see through cosmic dust and capture light from the first stars and galaxies formed over 13 billion years ago. After years of development, delays, and budget adjustments, the telescope finally took its place in space. One of the James Webb Space Telescope's most remarkable features is its primary mirror, which is 6.5 meters, 21 feet, in diameter. This mirror is composed of 18 hexagonal segments made of beryllium and coated with a thin layer of gold to enhance its ability to reflect infrared light. The large mirror allows the James Webb Space Telescope to collect more light than any previous space telescope, significantly improving its sensitivity and enabling it to observe faint, distant objects. The telescope's location in space is also a critical aspect of its design. Unlike the Hubble Space Telescope, which orbits Earth, the James Webb Space Telescope is positioned at the second Lagrange point, L2, a location approximately 1.5 million kilometers, 1 million miles, from Earth. At this point, the gravitational forces of the Earth and the Sun balance, allowing the telescope to remain in a stable orbit and have an unobstructed view of deep space. To observe in the infrared spectrum, the James Webb Space Telescope must be kept extremely cold. Its instruments are sensitive to heat, and even the faintest warmth could interfere with its observations. To maintain the necessary cold temperature, the telescope is equipped with a 5-layer sunshield the size of a tennis court. This sunshield blocks heat from the Sun, Earth, and Moon, allowing the telescope to remain at an operational temperature of around -233 degrees Celsius, -388 degrees Fahrenheit. The James Webb Space Telescope is equipped with 4 main scientific instruments: the Near-Infrared Camera, NIR-CAM, the Near-Infrared Spectrograph, NIR-SPEC, the Mid-Infrared Instrument, MIRI, and the Fine Guidance Sensor, Near-Infrared Imager and Slitless Spectrograph, FGS, NIRISS. Each of these instruments plays a crucial role in gathering data across a wide range of wavelengths in the infrared spectrum. NIR-CAM, the telescope's primary imaging tool, is designed to detect light from the earliest stars and galaxies, capturing detailed images of cosmic phenomena that occurred shortly after the Big Bang. NIR-SPEC is a spectrograph capable of analyzing the light emitted by objects such as galaxies and exoplanets, allowing scientists to determine their composition, temperature, and movement. MIRI extends the telescope's reach into the mid-infrared range, enabling it to observe colder objects like distant planets, dust clouds, and comets. One of the James Webb Space Telescope primary scientific goals is to study the formation of the first galaxies in the universe. By observing objects billions of light-years away, the telescope is effectively looking back in time to when the universe was only a few 100 million years old. The data gathered by the James Webb Space Telescope will provide invaluable insights into how these early galaxies formed, evolved, and contributed to the structure of the modern universe. The James Webb Space Telescope is also designed to study star formation and the birth of planetary systems. By peering through dense clouds of gas and dust, the telescope can reveal regions where new stars are forming. In these stellar nurseries, the James Webb Space Telescope will observe the processes that lead to the formation of planetary systems, offering clues about how our own solar system might have formed billions of years ago. One of the most exciting aspects of the James Webb Space Telescope mission is its potential to revolutionize our understanding of exoplanets. The telescope's infrared capabilities make it well-suited to studying the atmospheres of planets orbiting distant stars. By analyzing the light that passes through these atmospheres, scientists can detect the presence of molecules such as water, carbon dioxide, and methane, which could indicate the potential for life. The search for habitable exoplanets is one of the most compelling scientific endeavors of the James Webb Space Telescope. With its advanced instruments, the telescope has the potential to detect Earth-like planets in the habitable zones of other stars, regions where conditions may be suitable for liquid water and, by extension, life. By studying the atmospheres and conditions on these distant worlds, the James Webb Space Telescope may bring us closer to answering the age-old question: are we alone in the universe? In addition to its deep space exploration, the James Webb Space Telescope will also provide valuable data on objects within our own solar system. The telescope's infrared sensors can study the atmospheres of planets like Mars and Jupiter, the icy moons of the outer planets, and even distant objects in the Kuiper belt. Its ability to observe comets and asteroids in great detail will contribute to our understanding of the formation and evolution of the solar system. One of the major advantages of the James Webb Space Telescope is its ability to operate in a wide range of wavelengths, from the near-infrared to the mid-infrared. This flexibility allows the telescope to study a diverse array of cosmic phenomena, from the birth of stars to the most distant galaxies, all the way to the formation of planets. Its broad wavelength range makes it a powerful tool for astrophysicists seeking to answer some of the universe's most fundamental questions. While the Hubble Space Telescope has provided stunning images of galaxies, nebulae, and other celestial objects in visible light, the James Webb Space Telescope will go even further by observing in the infrared, revealing details that Hubble simply cannot see. The combination of these two telescopes, one focusing on visible light and the other on infrared, will give scientists a more complete picture of the universe. The James Webb Space Telescope is also notable for its complex deployment process. After launch, the telescope underwent a highly intricate series of maneuvers to unfold its massive sunshield and mirrors. The deployment process took weeks to complete, with hundreds of moving parts needing to work flawlessly for the telescope to function properly. Engineers at NASA and its partner agencies designed the JWST with extreme precision, knowing that there would be no possibility of servicing the telescope once it was in space. The deployment was one of the riskiest aspects of the James Webb Space Telescope mission. Unlike the Hubble Space Telescope, which orbits close enough to Earth for astronauts to repair and maintain, the James Webb Space Telescope is stationed far beyond the reach of human spaceflight. This means that any malfunction or failure would likely render the telescope unusable. Fortunately, the deployment was successful, and the James Webb Space Telescope began its scientific operations as planned. The telescope's journey to its final position at the L2 point took about a month. During this time, engineers monitored every stage of the deployment process, from the unfolding of the sunshield to the precise alignment of the 18 mirror segments. This careful orchestration ensured that the telescope was perfectly calibrated to begin its observations of the cosmos. Once fully operational, the James Webb Space Telescope quickly began sending back stunning images and data, confirming its capability to observe some of the faintest and most distant objects in the universe. One of the first images released from the James Webb Space Telescope showcased a star-forming region with extraordinary detail, providing a glimpse into the telescope's potential for groundbreaking discoveries. In addition to its primary scientific goals, the James Webb Space Telescope will also help answer fundamental questions about dark matter and dark energy, which together make up the vast majority of the universe's mass and energy. By studying the distribution of galaxies and the structure of the universe on the largest scales, the James Webb Space Telescope will contribute to our understanding of how dark matter influences the formation of galaxies and galaxy clusters. Dark energy, a mysterious force that is driving the accelerated expansion of the universe, is another target for the James Webb Space Telescope. By observing distant galaxies and supernovae, the telescope will gather data that may help scientists understand the nature of dark energy and its role in the evolution of the cosmos. These observations could lead to breakthroughs in our understanding of the fundamental forces that govern the universe. The James Webb Space Telescope's ability to peer into the earliest epochs of the universe has the potential to rewrite our understanding of cosmic history. By observing the light from the first stars and galaxies, James Webb Space Telescope will provide a direct window into the era of reionization, a period when the universe transitioned from a dark, opaque state to one filled with light as the first stars ignited. One of the key scientific questions the James Webb Space Telescope aims to answer is how the first galaxies formed and evolved over time. By studying these ancient objects, the telescope will help astronomers understand how galaxies merge, grow, and interact with each other. These insights will provide a clearer picture of how the universe's large-scale structure developed over billions of years. The telescope's unprecedented resolution and sensitivity will also allow it to study the formation of stars and planetary systems in greater detail than ever before. The James Webb Space Telescope's ability to peer through clouds of dust and gas will reveal the processes that drive the birth of stars and the formation of planets, shedding light on how planetary systems like our own came into being. The James Webb Space Telescope's role in exoplanet research is another area where it is expected to make major contributions. By analyzing the atmospheres of exoplanets, the telescope could help identify planets with conditions that are potentially suitable for life. This capability positions the James Webb Space Telescope as a key player in the search for life beyond Earth. The data gathered by the James Webb Space Telescope will be shared with scientists and astronomers worldwide, ensuring that the scientific community can build upon the discoveries made by this revolutionary telescope. The telescope's mission is expected to last at least 10 years, but its contributions to our understanding of the universe will continue for decades. The James Webb Space Telescope represents a new era in space exploration and scientific discovery. It stands as a symbol of human ingenuity and the desire to explore the cosmos, pushing the boundaries of what is possible in our quest to understand the universe's origins and our place within it. As the James Webb Space Telescope continues to operate, its discoveries will likely shape the future of astronomy and space science for generations to come.